Hello and welcome everyone to Know Your Scientist series presented by Shama Ahmedabad Academy of Sciences. Today we have with us a gravitational wave scientist who is serving currently as an associate professor at IIT Gandhinagar, Professor Anand Sengupta. We welcome you, sir.
Thank you very much. Thanks for having me.
Yes, sir. So we would start with your early life. To the bio that I have and the more information that I have about you, I would first like to know when was the time when you decided that now I want to go with science. Tell us about your early life.
I was born in Dhanbad, which is a small town in Jharkhand. Now Jharkhand, it was earlier in Bihar. And I did my schooling in Dinobli School, which was one of the better schools in Dhanbad. It was a Jesuit school. And I was alright in school. And I was very motivated by some of my mathematics teachers. And who always told me that you have to learn geometry. And I used to think that, well, I know geometry already, circles and triangles and so on. Of course, later on, I mean, that was, that is what actually attracted me towards science. I didn't know that I'm going to be, I was going to be a scientist, to be very honest. I was very drawn towards computers from a very young age. And I wanted a career in developing software when I was young. But then when I went to better places like Kanpur, I came across people, and especially I heard a lecture by Professor Ashok Sen, who basically told me what scientists are and what they do, and that is when I think that was a turning point for me. When I decided that, well, this is a nice career worth pursuing, maybe even better than software. So yeah, that is when I was drawn towards doing science. But I didn't have a laser sharp focus on one thing. I just chose. I went on doing things that I liked. And this is where I landed. So I learned things which I enjoyed. For a while I even dabbled with experiments, and then finally, even when I went for my PhD, it was not clear at all that I was going to do gravitational waves. Because in my masters I had done a project on experimental science with Professor H.C. Verma, and when I went to take my interview at Ayuka, so they asked me, what are you going to do, what is it that interests you, and I told them that I wanted to do Mossbauer spectroscopy, because that's all I knew. So yeah, I mean, I've kind of followed the passions that have and opportunities that have presented themselves, and I'm very happy I did it that way. So yeah, I tried to learn and kind of immerse myself at that point of time, whatever was interesting. And I don't think that I was ever set on the idea that I was going to be a gravitational wave scientist or anything like that. It just happened that it was a very interesting topic, and I completely immersed myself, and yeah.
So shifting it towards today's generation, where, especially in our generation, in our early 20s. So as you said that you were not pretty much in laser sharp focus about gravitational waves. So what should be the mindset of an early researcher these days?
Yeah, I mean, I have given it some thought. I mean, of course, in retrospect, So I think what I want to say is that all the training that we have at master's level or undergraduate level, these are training in things that have already been done. Right? It's like the analogy with coloring book. There's already shapes made, and you have to color it. Nothing should go out of the line and things like that. But I feel that research is a completely different ballgame, and it has absolutely nothing to do with how good a student you were or anything like that. It helps, but it's a more I would say it is more like it's like writing, a very creative field. Right? So it's like, now that you know some basic ways of drawing hands and legs and things like that, now you have to create your own, picture, something original, something that asking questions which are interesting and can be solved within finite time, not a Hubble time. So it's a totally different ball game. So it takes a different, like you have to learn how to listen to your inner voice, which tells you that this is, well, when you talk to somebody or something, you hear your inner voice and latch on to that idea and you nurture it. उसकी परवरिश करनी पड़ती है. You have to nurture that little germ of an idea in your mind. Initially it is very difficult
to even recognize it.
To recognize it. But you learn how to do that. And then you learn how to kind of, nurture that idea, make it bigger and, and
increase its
into a
magnitude.
full, take it to its full potential, right? So I think to all young researchers, I think I see that they are swayed a lot by very strong
applied external field.
No, well, that is one way to put it, but they are swayed very strongly by very strong characters.
Okay.
In any university and college, if you take somebody coming from Aligarh Muslim University, we have a very strong particle physics group over there, and I've interviewed so many of them, and they will say that, oh well, you have to, what do you want to be? I want to be a particle physicist, right? Similarly, most of the places in Calcutta, they want to do early universe because they have a very strong, they are swayed by very strong, characters. In every place there are such. I think one has to recognize your own aptitude. I think that's very important. I mean, now that I can look back, I think the best way is to match your aptitude with what is interesting. And then it's a match made in heaven. There are a lot of interesting things that you can think of and work with. Whether it is computers, whether it is pen and paper physics, whether it is experiments. Unfortunately, experiments are not taught very well in our country. And they are looked down upon as second-rate, science, because, it's cheaper to teach pen and paper physics. And there is this very, hierarchy of theory and then data and then experiments and so on. But I think that is complete nonsense. One should, so for young students, who are getting into this regime of research and a career in research, I would say that, don't get swayed by characters. Listen to them, but then, you should be like a sponge, absorb everything, and then match it with your aptitude, with your vibes, what excites you. And if you're good in something, go for it. That's what I would say. That's
Great
what has worked for me too. Right?
Beautifully explained.
Thanks a lot. I hope this message goes out to the
I felt it
for
myself personally right now.
Yeah. So and the other thing that I said, I want to just spend a little bit more time on this. I tell all my students, even my own MSc students and graduate students, that if you're doing a project, you're not married to it. Many people take it that yahi hai, bas, all my life I'm going to do that. But research experiences are like, you're developing your muscles, and then you'll find that one thing that matches your aptitude and your ability to develop those questions. So a good researcher is one who has who has brilliant ideas, questions, a bag of questions. And then, if you give a question to somebody, they are very well trained, anybody can solve it. But the crucial bit is to be able to develop and nurture questions. I think these are very important. And nowadays, people, you need ideas from many disciplines all at once. So I tell all my students to kind of put it somewhere at the back of your mind. You never know what will come in handy. I mean, it has happened to me. For instance, I've heard a talk when I was 20 years ago, and while doing some work, that has come in handy. It's not
Planned.
it was not planned at all. That's right. It was not planned. But I now realize, just being there in the room, half understanding, half completely confused by what the speaker was saying, it has helped me a lot. So I would advise students to be more mindful. Nowadays I see a lot of specialization, very narrow domains, and even people who are doing gravity, they just don't talk to each other much. They don't attend other people's seminars and so on. In a place like IIT, we have that luxury, we have talks from computer science, from material science, materials engineering, from physics, mathematics, all sorts of things, in one place. I find that is a good opportunity for, Similarly, a university is a great place for that matter, because, it's a melting pot. There are various people trying to do their own thing, and I think that gives you the breadth with which you can kind of conceptualize a problem and nurture it. I think that ability to do that is more important in research than being able to derive an equation and solve 10 problems from a textbook. It's important because it's like building muscles, as I said. But at the end of the day, it's a creative field. Okay? It's like thinking about a new poem or a new, something creative, right? And you cannot say where it came from. The germ of that idea, you may not even know when it was planted. So you have to keep your antennas, working overtime, so that when that happens, you latch onto it, and don't lose that.
Got it, sir. You spent a lot of time with gravitational wave studies.
Yeah.
So, starting with basics, what I understand about gravitational waves is about how one massive body interacts with another using this space and time. Expand my vision about it, sir.
Right.
Please, about what is it and how do we detect it?
So two questions here.
Yeah.
So what are gravitational waves? So the easiest way to think of it is that the Einsteinian way of looking at gravity is to not think of forces, but think of the curvature induced by the masses. Now, if those masses are dancing around doing some dynamics, the state that they set because of their heaviness, the massiveness, that state changes dynamically.
Okay. Yeah.
So now if I have a compact object here and it's doing some dynamics, it's going to disturb the curvature that it has induced because of its mass. Now this curvature is first induced locally, but then this curvature can be shown to travel out. Right? So for instance, if I have a black hole here, and this black hole warps the space-time around it, but if this black hole is moving around, so very far away from this black hole, it's a flat space-time. Right? But now if this black hole does some dynamics, the space-time locally gets disturbed.
Disturbance will travel.
And this disturbance travels out. So even far away, where it was a flat background, you will now see a disturbance riding on top of that flat background. So that is gravitational wave. So it's not like something that travels. It's very different from, say, a sound or light. So the stage itself is moving. It's dynamically changing.
Now I understand.
The geometry is changing.
Why it is difficult.
So yeah, it's a bit abstract, and so we have to do a lot of hand waving basically to and now once you have other things embedded in that far away space time, so they kind of feel the geometry has changed, right? So it's like dancers, they are on a stage and that stage has wobbling around, so their dynamics also changes. So that's how they feel the effect of gravitational waves. So yeah, the thing is that these gravitational waves couple very, very weakly with ordinary matter. it's a good thing and a bad thing. Good thing is that because they couple very weakly, their energy doesn't get dissipated, so you can see things from very, very early in the universe, for instance, if they're coming to you. Bad thing is that how do you detect something that doesn't couple? Okay. So, for instance, you can detect light, like you have these cameras and they are detecting light, because light couples very strongly with electrons, for instance, with matter. Light couples very strongly with that. But so you can make a very sensitive, uh, detector which can detect light and then create the current and which you can record and so on. With gravitational wave, it's very difficult. It doesn't couple. The coupling goes as the fourth power of the speed of light, inverse of.
Magnitude.
So 1 over c to the 4. So it's a very, very small number. So therefore, what happens is it's very difficult to build a detector which can record gravitational wave. Although there is a fantastic amount of energy in it, because space-time is very stiff. If you can imagine a stiff spring, it will take a lot of energy to move it a little bit here.
Yes.
So when a gravitational wave travels, it's like a very stiff spring
Moving.
that is getting disturbed. And, so there's a lot of energy in it, but the coupling to ordinary matter is very less. So, for instance, if you look at some of the promising sources, the amount of energy is the same as Jupiter in optical light. For instance. In Jupiter, you can stare at it with the naked eye.
Yeah.
And that light you can record in your eyes and see it. But so there's a tremendous amount of energy that is coming to you.
Coupling is less.
Yeah, but coupling is less. So therefore, it has taken a lot of technology to make a detector that is sensitive enough to record these events. And it has taken almost 40-50 years of effort to get a detector from its conception by Professor Ray Weiss and Kip Thorne to finally when we detected it in 2014. So it has been a long journey.
So tell us more about this interferometer. How did it detect and how did we develop it?
Well, historically, the earliest detectors that were made for gravitational waves, they were what I call mass interferometers, resonant mass interferometers. So the idea is that gravitational wave is carrying energy. You have this large piece of aluminum. It kind of dumps all its energy on that aluminum and excites its resonant modes. So if it's a cylinder, as we know, there are two resonant modes. One is the common mode, so the whole mass sways together. The other one is the differential mode. Now what you do is, of course, it moves very, the amplitude is very small. So what you do is you couple it with another resonator, which is much smaller. So this large resonator, which is very small amplitude, but all of the energy has dumped here.
It will move that in a large magnitude.
That will move, that couples to another resonant
smaller.
So it moves, the amplitude can be amplified.
Yeah.
That was the idea. But they are very narrow, resonant, because it resonates only at a single frequency. So 1000 hertz. 1000 hertz is good because then, why 1000 hertz? Because some of the supernova, they are spinning at around that frequency. So if they blow up, hopefully we'll see all the energy dumped at that frequency. But then Ray Weiss came up with this fantastic idea of using lasers or a Michelson interferometer with Fabry-Perot storage arms, which was a broadband detector. So, for instance, if a black hole coalesces, in spirals and merges, the gravitational wave is emitted over a, vast bandwidth of frequency.
Okay, yeah. Because it's the whole process of it.
Yeah, so it spins faster and faster, so the gravitational wave frequency becomes higher and higher. So you become sensitive over a larger bandwidth of frequencies, so it's not a single frequency. It's sensitive now over a large range of frequencies. So, and that was soon found to be a much more, promising way of detection. And light, you may think that, well, everything stretches, so maybe the frequency of light is also stretched, so how the hell do you measure it? You have to think over what time scale things are changing, right? So by the time the gravitational wave passes through, the arm length changes over a much smaller, uh, length time scale than the laser itself. So basically, the laser frequency is much smaller than the gravitational wave wavelength. So it can scan this cavity many times before all those effects come into play. So it's very interesting physics, and so that is how we are actually now able to measure gravitational wave signals. Yeah. So we have now measured almost 200 of them. Not all of them have been published, but the catalogs are being made after vetting each one of them and then extracting all the possible signs that one can out of them.
As you mentioned, light may stretch. We may think that
Sorry?
light would be stretching. So, how does relativity affect this?
No, this is all within the framework of relativity only. I mean, for instance, there is no space-time curvature in
We do not consider
Newtonian.
relativity.
There is no gravitational wave in Newtonian physics. The reason being that when you write down the equations in Newtonian physics, there is no time.
Yeah, X, Y, Z.
Right? So basically the grad square phi is a Poisson equation, is equated to the distribution of matter.
Yes.
So if you change matter somewhere, the potential is updated instantaneously everywhere in the universe, everywhere.
Okay.
So it's not that the potential gets updated in the form of a wave. So it doesn't work. There are no gravitational waves in relativity. It's a fallout of the geometric picture of gravity. That has been tested in many other ways. This was, I think, the last bastion, and that has been proven to be true as well.
So you had great experiences after your PhD, Cardiff University, UK, and then Caltech. USA.
Yes.
So, what are major differences in research culture there and in India?
I see. So yeah, I mean, I had a great time in Cardiff. Professor B.S. Satyaprakash, who is one of the world's leading figures in gravitational wave research, he was heading a group in Cardiff University, and I applied and I was interviewed, got through there. Big thing is that, big difference is that, of course, there's a big difference being a graduate student and as an independent researcher. So there's nobody to look. I mean, you have to basically fend for yourself. You have to find problems. Again, it's like you're
At your own.
trying to find problems. Of course, you can always talk to Satya. So that was a big difference I found. So that was one big difference. And as far as the research, atmosphere is concerned, I think people are much more independent there. Even graduate students, they of course discuss with their supervisors, but there is a better work-life balance, I would say.
There.
Yeah, of course. I mean, somehow I found that you could get more done in a week and still have time on the weekend to have fun, whereas that was not the case in India. I find that that somehow we work far more here and still not get enough done. I don't know why that is the case, but it was more efficient working abroad. But I guess it's a question of getting used to. I think. For instance, when we came back from after the postdoctoral fellowships, you get into this when you join as assistant professors and so on. there are also a lot of other responsibilities that come up with that position, which wasn't the case when we were postdoctoral fellows. So we were like, unbridled, research opportunities. So you could do whatever you wanted. Every Friday and Monday there would be meetings. You would meet graduate students. You'd help them. You'll attend teleconferences almost every day with different groups. It was really fun time. Very very intense work. But then also you have these other fellows who are also competing with you in a good way. I mean,
Healthy competition.
healthy competition, and you could bounce ideas off each other, and I think that stimulates you to find new ideas, work hard to get to the results and so on.
Miss that in India?
I don't say I miss that in India, but no, definitely I don't miss that in India. It's a different way of working in India, I think. But it's, as I said, I mean, I find myself working even on weekends uh, and still won't say as efficiently as I was in.
Say if we want to bring CAD-Tech in India, CAD-Tech work culture, how would we? Let's say you are the authorized.
I wish I knew the answer to that question. Honestly speaking, it's a very good question actually, and it's not just money. I think you have to put a lot of talented people in one place and let them, give them the freedom without the pressure. Of course, there is a latently. I mean, there is that you have to publish. You have to come up with ideas in a set interval of time. But then it's also this, feeding off each other's energies. Which is kind of so useful.
Positive feedback.
Very positive feedback.
Creativity doesn't work with deadlines.
No, it doesn't. It doesn't. In fact, it kind of stifles. Of course, I mean, I cannot say that you cannot be you can be completely absorbed of deadlines. It is part of life. But yeah, I think we had much more freedom to work, and I think I enjoyed that very much. Yeah.
So in your early years, science in India. Let's just come back to India for talking. So in your early years, when you decided, as you said that you took all the opportunities one after another which seemed interesting. So how did you look at science back then, and how has your perspective changed looking at science now? Has there been any big difference?
I think we have made a lot of progress. I won't say that people were not working then, but I think now, see, there were very limited areas of physics then. Now, a lot of new areas have opened up, which are very exciting. And there are these big projects that have come up in India, which we are spending a lot of money on it and so on. I think that has become, made a distinct change in flavor. I think we are a much more confident bunch of physicists now. Earlier, I was not privy to, I mean, earlier generation of students, we were not that conversant with what other people were doing in science. Unlike, you guys are very lucky that, you have, I think it moves with the times. We have moved on with the times, and I think now we are much more, we know what people are doing. I have students who come into my room and ask us, what do you work on?
Right.
That was not the culture then. So we kind of relied on what people told. Now I find that people are more frank, and people are taking on problems that are very difficult, and I think that's good. A lot of good science is happening in India. Big projects are coming in India, especially in astronomy. I think we are one of the leaders as far as world astronomy is concerned. We are like definitely a good thing. SK, LIGO India, TMT, huge projects, right?
Yes.
We are also building these amazing telescopes in Hanle. We are making plans for having space-based missions,
Yes.
Aditya L1, and so on. So I think a new brand, very very confident.
Getting ready.
Getting. I mean, I think the next generation will be even much more, confident, and I have I have good feeling about the way they.
I was asking about you are in this campus for like now 13 years.
Yeah.
So I was asking about your contributions, the contributions that you are proud at.
Okay, so I mean, I have been working for the LIGO Scientific Collaboration for the past 20-25 years, and after coming here, some of the things that we have done are contributions to the search pipelines. So, for instance, we, along with my graduate student Somen Roy, we basically provided the efficient template banks. So, gravitational wave data is actually matched with gravitational wave signals, and we create these banks of signal shapes, and the data is matched against each one of them. And there are geometric ways of constructing these banks, and we created these template banks which are now used for all the searches basically. So that was one of the things that me and my graduate student we contributed. We also contributed towards finding the higher harmonics of gravitational waves. So that was another work that my students and I carried out. So higher harmonics is like, you play say a note on the keyboard, and the higher harmonic of gravitational wave is the fifth after that. So it's like sa and then pa. So do you know the keyboard?
Not exactly about the music, but
yeah, so it's like, it occurs a fifth, saregama pa, so fifth note.
Yeah.
Except that the fifth note is very faint.
Okay.
So the dominant harmonic of a gravitational wave is, has the most energy. But if the two black holes have asymmetrical masses, then there is that higher harmonic also playing along with it.
Okay.
And although it's not important for the search, that means, but you can infer properties of that black hole much better if you include that harmonic.
Okay.
So we, along with 3 other groups in the world, we were the first to develop an algorithm to pull that out of the data. So unequivocally you could see there's a big peak at Sa and a little tiny peak above the noise at Pa, so we were able to pull it out.
So that little tiny peak.
That little tiny peak corresponding to the octopolar mode.
Oh.
So the dominant is at the quadrupolar mode. As you know, gravitational waves, the lowest order in which it radiates is at quadrupole. Unlike light. Light is a dipolar field.
Yes.
So quadrupole, and then the next octopole mode was we discovered that. Of course, the paper was written, it was a contribution from the entire LIGO Scientific Collaboration, but our contribution was in that paper was to
identify the pa.
Yes, identify that harmonic. There are other, for instance, we have also developed fast data analysis pipelines. So for instance, if 2 binary neutron stars merge, that signal is very long. It lasts for about 300-400 seconds in our data. But what we are interested in is not only discovering the signature of that signal, but also tell where in the sky it occurred, because when 2 neutron stars merge, it comes with a flash of gamma rays.
Right.
And you want to train all your conventional telescopes to quickly point towards that.
Right.
So if you take a day or two to figure out where in the sky it happened, by the time this is a transient signal, so the light could have become more and more faint and you would not see anything.
Yes.
So you need almost real time identification of the location in the sky. Sky localization is very very key to this is what is called your multi-messenger astronomy. So you're getting messages from 2 different branches of astronomy, and you kind of merge together to find discover new things.
Right.
So my students develop these fast parameter estimation pipelines to kind of do this work, and it becomes more problematic for space-based telescopes.
Why is it so?
Because space-based telescopes are going to observe the signal for a very long period of time, and because of which the antenna patterns, they become functions of time. Okay. So it's like you are watching the same thing. So suppose I am watching this Nilgai, right, and I observe it for a few seconds. So Nilgai will appear in a certain way.
Right.
But now if I go around it,
And it will
I'll
change the
see it,
position.
it will, the way I record the picture, that will change. So the antenna patterns change.
Right.
So I have to take into account that in order to
Identify where
make
is
sense
it.
of the data, right?
By the time it will change
Yes.
for our neutron star.
Yes, yes. So it comes with lot of positives because we can we can do fantastic science if you can observe it for a very long time. We can test general relativity.
Okay. But I guess we have enough proofs.
We have, but that is how science works. I mean, you are always probing. You are putting it through smaller and ever so fine tests of gravity.
Yes.
And the great thing is every time it comes out with flying colors. That is the big thing, right?
Yeah.
So, so if you observe for a very long signal, basically what it means is that you observe many cycles of the gravitational wave, and if your model say is different from what general relativity is supposed to be by 1 part in say a million, if you observe a large number of cycles, it's going to all add up, right? And you can see those differences much more prominently. So that gives us a unique laboratory to test general relativity, which you wouldn't be able to do otherwise. So as you said, our group has been working on developing these fast PE algorithms. I'm also very interested in applying computer science ideas to this. For instance, one of my students, he used what are called random projections. So you have data in a very high dimensional parameter space, and you use random vectors to project them into lower dimensional space, which makes the analysis much more tractable. Okay. And we did that and showed how to do this. So you can basically make a little ball out of the data. As I was saying, after coming to IIT, one great thing that has happened is, there are people from the computer science department. Okay. So they develop very, very, abstract ideas, and they're always looking for some application for their techniques. So I was very fortunate to meet Professor Anirban Dasgupta here, and I learned a lot from him, about these random vectors and random projections. Okay. And how they can be used for very, very computationally intensive operations like analyzing gravitational wave data. So that is another thing that we have developed over here. Right now we are also interested in projecting the science for an Indian space-based detector, a hypothetical detector which has not yet flown but may fly. Okay. So we are interested in projecting the science case. So imagine a situation in say 2038 where the other LIGO detectors may be down for upgrades. Okay. And only the Indian LIGO is operational. Great. And suppose together with that we have a decihertz, so 1/10 of a hertz, decihertz detector in space. Okay. An Indian decihertz detector in space. So now what kind of science could you do with the synergy between these two detectors? So that is something very fascinating. Yes. And we are, together with my students, we are trying to understand what kind of projections can you make. Can you measure certain things better? Can you say something about the distribution of binary black holes in the universe? Okay. So those are very, very
fascinating.
Very fascinating. Of course, it is fascinating, but also difficult questions to answer. But of course, we would have retired by then. but we are trying to lay the groundwork now,
Right.
and so maybe people like you take up the flag after we are gone to kind of continue that. So that is how science progresses anyway.
So, sir, I loved the analogy between the gravitational wave, sare gama pa.
Not everyone has a musical ear. You see, I mean, sometimes these analogies may backfire if you are not, because it may completely pass through the person if you
Right.
don't know. I mean,
But in science, I've mostly seen that science and arts grow together for a
Yes,
person. Mostly,
yes.
I've,
True,
what
true.
about I've learned.
That's right.
So, what would you? What are your thoughts about science and arts growing together?
I think, as I said right in the beginning, doing science or doing any science, I mean, being a researcher in science is exactly like,
Creating a poem.
writing a poem. There is no difference. Actually, it's as being creative. That's all, and you have no idea where that idea may strike. Okay, so I see no difference at all between these two fields. In
Great.
fact, of course, I cannot. I mean, I think that is where my analogy would stop. But you get my point, right?
Yes, yes,
I
sir,
mean,
of
so
course.
it's a creative field. I mean, it has nothing to do with whether you are able to solve this integral well, or how to solve that particular problem well or not. I mean, those things help. If you have an idea, of course, you would need the technical skills to solve it.
Right.
But getting the idea is more important. Okay, and that idea it's very hard to pinpoint that, no, if you do this you'll get an idea. That's not how it works. You have to talk to people. That's what I tell my students also. Just talk to other guys, tell them what you are doing, learn what they are. You may not get 100% complete picture,
Right.
but that kind of stimulates some parts of your brain, which
Gives more authenticity to your own idea. Like,
yes, and also I find that all the good scientists that I have met, they are very good in arts as well. They are very deep into arts. Some of them write. Some people, they have skills in other forms of art, and it's I think I don't know for sure, but I think the part of the brain which leads to these things are probably the same. Yeah, it's just
that explains your musical journey.
what journey?
As in you being so good at music, and
I'm
I just
I mean, well, I have a very deep interest in classical music, and especially I've after my PhD, I was in Pune,
yeah.
and Pune, as you know, is one of the centers of classical music in India. And I have also had the fortune of meeting a lot of people, who were far more talented and far more into these kind of things than I was. And like a sponge, I just absorbed it, and I became richer for that. Okay, so yeah, so I think that is very important to kind of continuously absorb things. So, for instance, when I had absolutely no exposure to Western music.
At that time?
At that time, when I went to Ayuka, there were people who just showed me how beautiful it was, and that's how, you kind of continuously absorb.
Right.
And these guys were so brilliant, they were good in maths, they were good in music, they were good in literature, and that really, set the scene over there. And I think it really helps to be in that kind of an atmosphere. To develop new questions.
My next question goes like, in this series of detectors that we are making, or the observatories, I think we are making an Einstein telescope for the same.
Yeah, that is one of the European next generation detectors.
Okay.
It's a third generation detector, as we say.
Okay.
So it was initial LIGO was the first generation. And then we have these advanced LIGO which are working now, which is the second generation detectors. And then we have the third generation ground based detectors. So Einstein telescope is one which is being conceptualized in Europe. And the advanced LIGO will also go through a third generation upgrade. Cosmic Explorer, that's right.
Cosmic Explorer.
Cosmic, I hope you can cut all this
You
out.
just speak for once. It's Cosmic Explorer. We'll cut it.
Yeah, so the third generation advanced LIGO will be called the Cosmic Explorer.
Okay.
So they will have almost 10 times better sensitivity than even current generation detectors. But you see, all these plans are based on projections of technology 10 years down the line. Some of that technology which is being projected doesn't even exist right now.
Okay.
So, it's like a bit of crystal gazing,
Extrapolating stuff.
extrapolating from what exists
We are doing right now.
right
So
now.
we might be proved even faster than what we extrapolated, or might not. We might be slower.
Well,
than
I would be more, cautious than that. But
Okay.
yeah, even if it happens in 10 years down the line, I think it's worth.
Great.
But all of this is a projection. You see, none of that technology exists.
Right now. My main question was, how is it different from the technology? How is it different from what we have right now?
Oh, technology wise, well, I'm not an experimentalist, so I could not possibly give you a very detailed, difference. But some of the new technologies that are going in mainly involves seismic isolation.
Okay.
So one of our limiting technologies right now is how the ground motion couples to the detectors, because of which we cannot go below 5 hertz.
Okay.
Below 5 hertz, the ground shakes so far, so much
Vibration.
that the energy due to the noise of this motion that completely swamps out any gravitational wave signal. So and all the action seems to happen at lower and lower frequencies, right? So that's why we want to go to space for a decihertz detector,
Okay. Got it.
or LISA, a millihertz detector.
Okay.
So ground-based detectors, I think they are going to have new lasers, new seismic isolations, even cooling. So for instance, one of the sources of our noise right now is that these mirrors, which are our test particles, they are actually at ambient room temperature.
Okay. We have to cool them down.
But if you want to cool them, that HVAC system which is going to cool that mirror,
That will also.
that will add noise to it.
Right.
So how do you cool without adding noise? It's going to be a challenge. But yes, these are some of the things that are. So we expect that once these things are sorted out, we'll have 10 times better sensitivity and go all the way up to 1 hertz even.
Okay.
So right now, whatever sensitivity we have at 5 hertz, we want to push it down to 1 hertz. So that's going to give us so the signals will last for hours now.
Right.
And we are also going to be sensitive to much more heavier black holes, which we cannot see with the current data. So the heavier the system, the faster it evolves in frequency. So that's why in LISA we are going to observe supermassive black holes, but we cannot observe supermassive black holes with LIGO.
Okay.
Because they are too heavy. They would evolve much faster.
Right.
And by the time you reach 10 hertz, which is where the sensitivity of current LIGO is, all the signal would have gone. You are not sensitive to that anymore. So we are now sensitive to stellar mass black holes.
Okay.
So yeah, we can push it down to about 1 hertz.
Great. Sir, people my age, let's say people in early 20s, are taught about work-life balance in a way that don't think about work-life balance right now. You can have it later. Work all in. What are your views on it, based on the Caltech culture that we just discussed?
No, it is not based on Caltech culture, or it's like, see, you should enjoy what you're doing. Then it doesn't feel like you are working super hard. If you work in a field which is exciting for you, you cannot wait to come to work next day. When you are going back home, all the time you are kind of decimating the ideas that you had worked on that same day. So it's like it becomes your existence, a whole existence, right? And it's fun to work with. So then it doesn't feel like exhausting or energy draining at all. Somehow it kind of even pumps more energy into you, right? So yeah, I feel that once you're in that state of mind, sometimes when we work on certain projects, it feels like that. So you get supercharged.
Right.
So I think then it doesn't feel like your
work and life are no different. They are only one thing.
But of course, you have to give time to your family and your partner and so on. So That is important. But I think these are dynamical things. It's not. You will have times where you have absolutely no idea what you are doing, and interspersed with that, you will have moments where you get these sparks. So which may or may not work, but at the end of the day. But yeah, so those moments are what
Life is about.
work definitely.
So that now we are in your office cabin. So that now we are in your cabin. I would like to know about your personal side more. What do you do except for physics to unwind?
Oh, a lot of things. So, none of them very well, but I have quite a few interests. For instance, music is one. Although it's too late to learn any new instrument, I have started learning to play the guitar. I play other musical instruments, but this is not, this is just for my own satisfaction. The other things that I do is I'm very, very interested in a lot of poetry of various kinds. So I read a lot of poetry. Wisława Szymborska, for instance, is one of my most favorite poets. She is Czechoslovakian, and she has written a lot of poetry about World War II. And I think that is fantastic. I read a lot of ghazals also, although I don't understand a lot of the very difficult words. But nowadays there are so many ways of figuring out what they mean. And I used to write, but I think that has dried up. I don't write anymore. But yeah, those are the kind of things I do. Recreationally, I like recreational statistics. So that is something that I do on my own time.
That's a new word, sir. I would want to throw light upon it. What's this recreational statistics?
Recreation for me.
So,
for instance, I find that statistics was and still isn't taught very well at to physics schools. This is something that allows. It's a tool that it is so powerful for inference and for various other things. There's a lot of geometry that gets into statistics. This is something that I think should be taught well at master's level because it opens many doors for research. At least in my experience, that I found that to be true. And luckily, my supervisor was a student of mathematics, and I got it from him. Of course, I nowhere close to what Sanjeev Dhurandhar can and do and so on. But I like to kind of read topics on statistics and write little codes to kind of understand what they mean and things like that. So yeah, keep myself busy.
In the answer to first question, you told about how learning and the time to learn. You told about the age to learn.
Yeah.
Do you believe that there is a certain age to learn?
Well, see, when you learn music to play things, it is a lot to do with developing our muscles, memory,
Right.
to play these things. When you are younger, I think it's easier to develop those kind of things. You don't have to put in a lot of conscious effort to move your fingers in a certain way.
Right.
As you grow older, I think
Flexibility.
decreases, but it's a lot of fun.
So, always is. Making it a little bit serious. Say there is a child growing up right now, and as we talk about this flexibility. So, what would you, in general terms, guide to the parents to make him learn about things? As you said, that this flexibility is something that
you should be open to all sorts of things. You don't know what a child is. What kind of aptitudes the child has. So I think in Bengal I have seen that children are generally exposed to a lot of art at a very young age, like painting, singing, dancing, lots of things, and I think that is very good because it develops, I think, your ability to comprehend other areas also. I think I'm speaking way beyond my expertise here, but I think personally I find that it kind of it helps people to comprehend things, abstract things, when you learn music and things like that.
Okay. As we were talking before about there is a saturation of learning new things, like you talked about this e-currency thing, that is a limit, the saturation.
That's
about each
right.
and every generation has their saturation of knowledge.
Yeah.
So how do you accept that with time? As for someone at my age looking at stuff, we always have this, at this age we have this, we can do everything, we can do anything, we have this scope of improvement tends to infinite.
Yes.
How does the graph go with time?
With a lot of sadness. But yeah, there is. I mean, I think with age, I think the capacity to learn also decreases a little bit. It is true, but as far as research is concerned, I think you can still stay young if you are talking to the right people. Okay, so if you are active, new ideas spring from that activity. So for instance, if you are working on a problem, then I have found that new ideas are generated from that problem itself. Whereas if you are not active, for instance, for whatever reasons, you are having a rough patch, your creativity is not, we all have. I mean, even writers have these so-called writer's block. So if you are in that situation, it's very difficult it gets progressively more and more difficult to get into, stay active.
Back to the lane.
Right. So if you are active in research, it keeps you young, because you are always, putting your ideas in front of others, learning from others, and it keeps you young in that sense. So new ideas come from
staying in touch with
the field, actually. So I had a phase like that, and one of my mentors, Professor Bala Iyer, I have to mention this because he told me that I told Bala that, look, I'm not I'm going through a rough phase, and Bala advised me that, look, you have to find the time, 8 hours in a day, where you just lock yourself somewhere and get into read research papers, do your own work, not be bothered by other things. So I think that sort of you have to also have that sort of what should I say, discipline to force yourself to concentrate, and that also helps to kind of develop new ideas. As I said, I mean, like, a lot of people do PhD and they think that, oh, you have solved 3 problems, written 3 papers, that's it. But that's not it. You're solving somebody else's problem. You're solving your supervisor's problem, the problem that the supervisor had thought of. In many countries that's not the case, but in India that seems to be the trend. The training is actually for you to think of your own problems. That sustains you for the remaining 30 years of your life. Okay. So I think that's my advice to all PhD students also who may be listening to this, that while you are developing the technical expertise to solve certain kind of problems, the focus is not that. The focus is to think of. So I tell my PhD students, for instance, especially towards the end of their 5-year PhD periods, that when the day when you come to me with a problem that is interesting and can be solved within how much time, I would say that you are ready to start writing your thesis. So I think that's a pretty good, decent way of judging whether you are ready to take on the world.
Great, sir. So physics, as far as I've seen, eventually leads to philosophy.
Yeah.
What are your thoughts on this?
Yes, well, most of the top physicists, the ideas have come from very deep-rooted philosophy. For instance, even when you talk about general relativity, that has come from very deep-rooted philosophy that was developed by Mark's principle and things like that. Unfortunately, when we are trained in physics, that somehow gets secondary importance over technical virtuosity. Okay, so a lot of physics that is taught in master's level is just a course on various ways to solve differential equations. Okay, so suppose I tell you that I give you a black box, and no matter how difficult the equation you throw at it, you get can solve it for you. I think the real learning starts from there. Okay.
Which equations to throw to it?
Yeah, no, not only that. How do you come up with what does it even mean, right? To write an equation like that or in a certain way. So I think that part is not transferred so easily because a lot of focus. For instance, think about a course on electrodynamics, right? If you look at a book like, say, book by say Griffiths, right? So almost half of it is just boundary value problems. I mean, you just develop different ways of solving boundary value problems. So I think it is important to develop technical virtuosity, but it's also very important to understand what it means. If you would be lucky to get a teacher who would, stress on that.
Given you the opportunity to change something about, let's say, education, BSc onwards, not let's say school,
right.
BSc, what would be the top 3 changes?
You put me in a spot here. So I would, connection with current experiments. Okay, so one of the feedback that I get, we teach physics to, say, BTech students, and one of the most often feedback that we get is that, all this was done in the 1600s. So they don't feel any connection. There's a lot of open problems, and there are a lot of interesting problems that have absolutely no solution, or a lot of new experiments that are coming up even today. And somehow we have failed to make that connection. Okay, so I think we have to also keep ourselves completely abreast of what is going on, the new developments. So it's difficult to teach it that way, but for instance, I would love to have courses on, what are the new experiments that are happening, right? You're a master student yourself. Can you name a single interesting experiment in the last couple of years that has been, caught the attention of, physicists?
The gravitational waves is the latest I can, and then
sure.
All we are being fed is based on Nobel prizes. So that's where all the information is coming to us.
Very important experiments, but even every day. I mean, for instance, recently there is this experiment called DESI, which is an experiment to scan the sky, and that has come up with fantastic results to show that dark energy is evolving in time. Now these are,
experiments we should be talking about.
Yeah, these are things that we should talk about in our classrooms, so that you have to kind of give them that vision, that grand vision. A lot of daydreaming is important,
right?
To be
not filling them in the boxes and let
important
them think
to
that
learn
there are no
technical
boxes.
virtuosity. Yes, it is very important, and it's very important. I'm trying to undermine that effort, but I think we have lost our touch with a lot of things that are happening right now in laboratories all over the world, and I think that information somehow has to be distilled, and so our courses also need to evolve. I feel it cannot be the same course that was taught to us. Okay,
Yes.
so it has to evolve with the times. We have to make an effort as teachers to for instance, in many PhD interviews, I ask them this question that, Higgs boson was discovered. So the idea in their mind is that, here is a Higgs particle that came, and then they somehow caught it, and something happened to it. And then I said that, it was said that this Higgs boson was discovered at more than 5 sigma confidence. does it mean anything to you as a physics student?
Not yet, sir.
But and yet it should, right?
Yes.
Because this is one of the most important discoveries of our times, right? So why are you not trained well enough to understand what this means? Because in the last 50 years of particle physics, this is probably one of the most important
Yes.
things that has come out, and yet we are unable to give you that ability to appreciate what that one line means. And it's not very difficult, trust me, it's not very difficult to explain what it is. So I think as teachers we have to also evolve to take on that challenge. And of course, as human beings we are very averse to change, but I think a little bit can be incorporated. So we have to move with the times. Very important.
Got it, sir. Concluding message to our viewers, young researchers and students from you.
I have only one message for them, which is that you have to marry your aptitude with the expertise that you want to develop. Okay? Different people have different ways of looking at physics. Okay? Some people can make fantastic electronics. Some people are very good in computers. Some people are very good at doing pen and paper calculations. Okay, so let no one tell you or box you into what is physics and what is not physics. Okay, and nowadays the other thing is we have to develop a mentality where these problems nowadays, the biggest problems in physics, cannot be solved by one person sitting in. It's not like Maxwell's time anymore. Okay, that you can be in the attic somewhere and then hide away and write your equations, and suddenly you appear before the world, and then here are these wonderful equations that you have. Those times are gone. So you have to develop a sensitivity that big science needs collaboration. I think this is something that again is not stressed enough. Collaborative approaches where you bring in expertise from different areas. That sort of a collaboration is needed to solve some of the biggest problems in physics these days. And so I hope the new generation can develop that sensitivity, that we need contributions from other people in order to do this interesting science. So people from computer science, people from mathematics, statistics, they are all needed. You have to learn these new techniques in order to survive. So yeah.
Got it, sir. Thank you. Now we'll conclude this, and it was great having you.
Yeah, I had a great time. Thanks a lot
Thank
for
you
having
very
me
much,
on your show. Thanks.